Wait, so, I'm sorry.
No, you're good.
So, for like D, the yes, yes, that the only way you would find that.
Wait, hold on. Guys, hush. Shh, shh. Say that again. Uh-huh. Wrong class. He was looking for a student in my other class.
Was it Nick?
So, no.
Wait, tell us independence.
No. No. Hey, y'all are nosy as crap. Hush. Butt out. What's up? Guys, can you shut up so I can hear this question? Thank you.
So how would we explain if it would be independent and would we have to like on the test?
So if it's not independent, that means that when you calculate the conditional probabilities, so like let's say cats and dogs, okay? Like let's say I want the probability of a person having a dog given they also have a cat. That means you would calculate the probability that they have a dog given they don't have a cat. If those probabilities remain the same, they're independent. If they're not, they're dependent.
And then for like the number 5 one, so I get the first one is yes. 5 times they're not independent, they're dependent.
So for our class, it's actually dependent because the probabilities do not match
But
up.
then 5 is independent.
Because the probabilities matched up.
And would that always be not, but would it be easier to find it because they have to find independence?
No, technically we did the exact same thing for both questions.
So
It was just written differently. Mm-hmm. And like I said earlier, I think you may have been in the bathroom, but even if you're looking at the same type of situation, depending on the data sets and the people that are in it, dependence and independence can go back and forth for something like this. So like for this case, in this class, it was actually a little bit dependent because just the makeup of the class. For the other class, it turned out to be independent. So that's why. All right, so conditional probability. So the probability of one event occurring changes depending on the events occurring. Then we say there is a conditional probability. So the language and symbolism for conditional probability can be kind of confusing, but the idea is fairly straightforward, especially when you're looking at that frequency table. So like we did in the warm-up. Okay, so this frequency table that we're about to look at is the same one that we did in the lesson yesterday. I think it was towards the end of the lesson. Okay, so it's that same 52 graduating seniors were surveyed for their post-graduation plans, and they were sorted by gender. So M is male, F is female, C is going to college, N is not going to college. So yes, so for letter A, the probability that they would be female, we're still just looking strictly at totals. So it would be 22 out of the total of 52. And if I simplify that, what is it? 11 over 26, good. And just for funsies, what is that as a decimal? Let's round to the nearest hundredth. 0.42, good. So guys, when it comes to whether you want to leave it as a fraction or change it to a decimal, it kind of depends on what you're looking at. Both have their strengths. The fraction is the easiest to get it into. A decimal can kind of tell you a bit more, because a decimal can tell you which one's more likely or not, especially if they have different denominators. What's the probability of that person going to college, or of a person that we randomly pick going to college? 29 out of 52. Now that won't be able to be simplified.
It would be 5 points, or it would be 0.56.
Right. So that's what it would be as a decimal. And the reason I know that 29 over 52 is not going to simplify is because 29 is prime. Okay. So now we are going to look at the probability of going to college given they are female. So again, this little symbol right here means given. And we're going to draw a Venn diagram to help us justify. So before we even calculate it, let's just make the Venn diagram first. Okay? So when we make a Venn diagram, what's the first thing I tell you always do first? The intersection. So how many people are both female and going to college? 13. How many total females do we have? 22. So how many are not going to college? 9. How many are going to college but they're not female? 16. Because how many are neither? 14. It's basically the males that are not going to college. That's the number. If I add up all 4 of those numbers, will that give me 52? It should. But does it? It does, yes. Okay, so if you're looking at a Venn diagram, here's kind of how you can think about it. So we want the probability of this student going to college given that we already know that they're female. So that means that if we're looking at the Venn diagram, we're looking exclusively at this circle, the female circle only. So how many total is in that circle? 22. So that's what we're taking it out of. And then how many within that circle is actually going to college? 13. So there's 13 within that circle that are actually going to college. Okay, so we have 22 females total within the green circle. 13 of them are actually going to college, which we can confirm using this table. But I just wanted to show you what. Yep. And that can't simplify because again, 13 is prime. But what is that as a decimal approximately? 0. What? 59. So when you're doing conditional probability with a Venn diagram, typically you're going to be looking at a specific circle of the Venn diagram. So it's usually whatever the given is. And then you look for the overlap. So if we look within this specific circle, we know there's 22 total if we add the 9 and the 13. And then the 13 is the actual overlap between female and going to college. So that's our probability, 13 over 22. Does that make sense? So back to using the frequency table. We are going to, which is more likely? A person picked at random going to college given they are male, so the probability of college given male, or a person will be male given they are going to college, so male given college. We're going to show the calculations for both. So let's do the first one. The probability of them going to college given that they're male. So if I go up back to the frequency table, I know for a fact they're male. So which part of the frequency table am I looking at? No, they are not. So I know for a fact that they're male, okay? So how many of those males are actually going to college? 16 out of 30. So there's 16 males out of 30 that are going to college. And that'll simplify down to what? 8 over 15. Good. And what is that as a decimal? 0.53. So probability that they're male given that they're going to college. So now if I go back up here, I'm looking at this row. I'm looking at the going to college row because I know for a fact that they're going to college. So how many are male? 16 out of 29. And what is that as a decimal? 0.55. So this is an example of why changing to a decimal is pretty useful because now we can clearly see which one's more likely, which one's more likely. Male given college. And why is that? Has a higher percentage or it has a higher probability of happening. So the one that's most likely is male given college is most likely. Or more likely, I should say. So that's an example why decimals will help you. So again, guys, if this was on your test, I don't care which form you give me the probability in fraction, decimal, or percent. The only time I will care is if they specifically dictate what they wanted it. So if they wanted a percent, you better give it to me as a percent. If they want it as a fraction, you better give it to me as a fraction. If they want it as a decimal, you better give it to me as a decimal. Okay? But they're all connected anyway. So now let's use that knowledge to come up with an actual rule for conditional probability for when we don't have that nice little handy-dandy two-way frequency table. Or a Venn diagram for that matter. So, but we are going to use a Venn diagram to come up with this. So calculating conditional probabilities are based off of counts. And these conditional probabilities can also be based off of other probabilities that we can find. So in a generic Venn diagram, shown to the right, each dot represents an equally likely outcome of a sample space. Some fall only in event A, some only into event B, and some in both, and some in neither. So to kind of help put it in perspective with my first period kids, I said that, let's say A was the number of people that had a dog, B was the number of people that had a cat. Okay? Actually, no, I flipped it. A was cat, B was dog. And the sample space was just number of people who had pets. Because, there are people that have pets that are not necessarily cats or dogs. Somebody may have a rabbit or a turtle. Yeah. So we're going to go ahead, guys, stop messing around. So we're going to go ahead and count the dots in each section just so we don't have to worry about counting them later. So how many people do I have in the only A section? 6. How many in the middle? How many in B? How many on the outside? All right. So, they want to know what is the probability of A occurring given B has already occurred. So in other words, what's the probability of a person being randomly selected will have a cat given that we already know they have a dog? So 3 out of 8. How'd you get that?
Because it's like the numbers.
Wow.
So insightful, Fisher. So if you look at the dog circle, because we already know that this person's going to have a dog, what's the total of the dog circle?
8.
There's 8 people total. How many of those also have a cat? 3. So it's 3 out of 8. So in other words, this was the number of people that had both a dog and cat, and this was the number of people that had a dog. And remember, that number of people still lumps in the ones that have cats as well, but they just happen to have a dog. Like if I just asked you guys who in here has a dog, I don't care if you have a cat as well, okay, because that's not what I asked. If I asked if you have both, then that's different, okay? Now, Based off of what we just did, let's see if we can come up with a generic formula that will always work for conditional probability. So essentially, what was the numerator?
The one in the middle.
The one in the middle. So how would I state that in terms of probability? It's the probability. It's the probability, the intersection of A and B. So the probability that A and B happen over, what was the denominator?
The number of
The number of dogs, or the probability of which set happening? B, or the given, yes. Over the probability of B. So if we want to put this in layman terms, it's the probability of A and B over the probability of B. And remember, B was what we were told was given.
So would it be just A plus B?
No, A and B is the overlap. Nope. Completely different. So this formula, like right here, is the actual formula for conditional probability. If you're trying to find the probability of, and remember, if you want to rewrite this, probability of A given B, that's equal to this formula. And think about it, it actually is true, because we have our intersection here, and then the probability of B happening total. If we look back at our previous example, the female going to college, don't we have the intersection here and then the total number of females? Isn't that true? Yeah. So it still works. Now, why is that important? Because sometimes they don't give us numbers, they give us probabilities. So this next example, even though they gave us a frequency table, this is known as a relative frequency table. Meaning they don't give us the number of people, they give us the probability of it happening. Probably.
So we just say 15, 25, like just make everything to where it's in number.
I wouldn't. I mean, like if you use the formula, it's pretty easy. It's a pretty easy formula, especially when you have the table already. Okay. So this survey examines the relationship between hair color and eye color. The chart shows the proportion of people surveyed who fell into each category. So in other words, they took the probability of people that fell into each category. So if you notice, what does the total of all totals add up to? 1. So that's probability. Okay? So it has the probabilities of a specific eye color happening, it has the probability of a specific hair color happening, and then it has the probabilities of the intersections of those happening. Okay, that's how you read it. So, how do I read this right here? What does that mean? Carson?
Well, that's like the total number.
No. How do I read that? In layman's terms, how would I say that statement?
He is the one that has blonde hair already, but also has brown eyes.
Okay, so that's one way to say it. What's another way to say it? Probability of brown eyes given blonde hair.
Is there going to be a question where we have to split it like that on close?
No, but I'm doing this so that you remember that that's a thing. Okay? And to be honest, I don't really need to write this because they already stated it here. Probability that they had brown hair given that they had blonde. Brown eyes given they had blonde hair. So, not quite. So, okay, hold on. So, first off, let's just write this out as a formula using the formula up here. But using these two events. So let's say that brown eyes was event A, blonde hair was event B. So if you use the formula that we just got in the previous question, what are we finding in the numerator? The probability of what? No. The probability of what in terms of the events? Brown eyes and blonde hair over what? The probability that they have blonde hair.
So yeah, wait, and then the
0.10 over not 0.35. Oh, no, yeah, it is. So, yeah, we would look at 0.10. I was looking at this 0.35, not this one. So, the probability that they both have brown hair and blue eyes is 0.10. So, I have 0.10 over the probability that they have blonde hair. So, we look at the total of the blonde hair, which is 0.35. So, what's that as a decimal? Let's just leave it as a decimal. So round it to the nearest hundredth. What is it about? So it's about 29% of people with blonde hair will also have brown eyes. So that's the probability. And again, the way you would say that is that given that you already know this person has blonde hair, about 29% of those people will have brown eyes as well. Yes. Okay, what about this next one? We know it's going to be red hair given green eyes.
you go to green eyes, minus 25, put that as the denominator. And then you can see how then it's 0.15. So that'd be the first, it'd be 15 over 25.
So we need the intersection first. So that'll be, yes, sir.
I gotta go get my pads and helmet for football for this spring.
After we finish lesson. Yeah. So I got 0.15 as the intersection. So we need the red hair. I'm just going to abbreviate this. So we need the probability of red hair and green eyes over the probability of green eyes. So this would be 0.15 because that's the probability of them both happening over what? 0.25, which is the probability of one of them happening. Or in this case, the green eyes.
That would be 6.
So if you put that in your calculator, what is that as a decimal?
0.6.
It's 0.6 exactly. Okay.
Yeah. Because you could take 25 times.
Yeah. You could times both of them by 100 and do that way and everything else. Yeah. Okay. Now here's the question: does having red hair have some dependence on having green eyes? So in other words, if we look at all the people with red hair, does having red hair mean that they should also have green eyes? In other words, are you sure?
Yeah.
How do we check? How do we check?
Yeah.
Wow.
Actually, it's like.
Think about what we did in the warm-up.
You do the opposite of it. Like a trend.
So you do the opposite of it. Opposite of what? Well, we know, but we're saying that red hair have dependence on green eyes, meaning that depending on whether you have green eyes or not, will change the probability that you have red hair. How do I check? We can't say anything until we know for sure.
You gotta do red over green. You have to do green over red.
Nope. Okay, look back at the mathematics. Look at how we looked at for independence, because obviously if it's not independent, it's dependent, because it's dual. But look at what they calculated. So we were looking at whether taco tongue, being able to do taco tongue, was dependent on the evil eyebrow or not. So what did we have to do for both those conditional? We got whether we could do.
If they don't have green eyes.
We have to look at if they don't have green eyes, given that they don't have green eyes. So we got so basically whatever the given is, you got to check that and its complement for independence. Okay, but the event that you're looking at, probability-wise, you keep that. So we keep the red hair as is. But we got to check to see if not having green eyes will change the probability of if you have red hair or not. So my conditional probability will now be the probability of having red hair given they do not have green eyes.
So what's the formula for
It's 0.5 out.
Independence, all you do is that so if you want the formula for independence,
is it overly common?
not really. So independence, if A and B are independent of each other, that means the probability of A given B is equal to the probability of A given not B, or B complement. That's what independence means. That's it. That's it. That's all you gotta do. You just gotta check to see if those two conditional probabilities are the same. If they are, they're independent. If they're not, they're dependent on each other. Okay, so that means that I gotta find the probability of red hair and no green eyes. So green eyes complement, if you want to put it that way, over the probability of them not having green eyes. So green eyes complement. So what's the probability of them not having green eyes? Nope. I mean, what's the problem? Yeah, it's 0.75 for if they don't have green eyes. Yeah, that's the denominator. How'd you get that?
Because it's 1 minus 125.
Yeah, so you can either subtract 1 and 0.25, because remember complements have to add to 1, or you could just add up the other two parts of the total column for eyes. So if you do 0.40 plus 0.35, you get 0.75. If you do 1 minus 0.25, you get 0.75. What's the probability of having red hair and no green eyes? I'm sorry, say it one more time.
0.05 out of 0.02.
It's 0.05. So again, you can add up the two columns of red hair where they have not green eyes, they have blue or brown. Or you could subtract the total from the green eyes. Either way, you'd still get 0.05. So if you put that in your calculator, what is that approximately? Or actually? No. Decimal. I want a decimal.
0.04.
5 divided by 75?
No, I did 125 because that's what
It's actually 115.
it is.
75 divided by 5 is 15. So what is that as a decimal? So do 0.05 divided by 0.75. I want a decimal.
0.06.
0.06 or 0.
0.06 for beta. It's pretty much 0.07.
0.07. Okay. All right. So 0.07 is that probability. So here's the question. Are they independent of each other, or is there definitely a dependency? There's definitely a dependency because these two are not the same. Not even close, actually. So yes, red hair is dependent on green eyes.
Whoa. So dependent just means they're not the same. Which